All right, why don't we go ahead and get started. So welcome back everybody to EE290C. So just a couple of logistical things. So basically I've posted phase 4, I think maybe a couple nights ago, right after phase 3 was due. Again, there should be no big surprises there. It's pretty much just finishing everything up. As a reminder, there will be sort of presentations before the actual final report is due. So the intent of that is to still, you should be pretty close to, or you should be hopefully getting very close to be completed with the presentation. But, you could still have some chance to modify things based on the feedback and stuff like that you'll get either from me or from the rest of the class. Just scheduling-wise, the last week of, let's say, normal lectures will be next week. The following week will be the presentations, and then the Monday after that is when Phase 4 report is actually due. So not too much time from now, but hopefully everyone is well on their way and, making good progress and all that. The other thing I'll mention is we are going to do the Eta Kappa Nu course reviews at the end of the lecture next Thursday. So that means attendance is going to be required because, I want to get the feedback and all that. So definitely need to show up in person next Thursday. And then obviously for the presentations themselves, again, you'll have to be here because if you're not here, then nobody's speaking, and that won't be particularly interesting. But in all seriousness, please do show up or make sure you show up both next Thursday and for the actual presentations the following week. So any questions on either logistics or just, class stuff or anything like that? Yeah.
Can you just assign the presentations ahead of time?
Oh, sure. If you guys want, I can. We can go in the same order as we went last time.
Or you can flip it to make things fair, or whatever.
Sure, we can flip it. That's fine too. So I think that actually, let's see if I remember actually the order then. So I think that means, then I'll just do one person, so that I have to write like a whole bunch of names, and let me just find some blank space somewhere here. I'll go to the beginning. Okay, so I think that means the first group will be basically Chintan's group. The second group, if I remember correctly, was actually, was it you guys, Ida, or was it? No, you guys were.
No, it was not us. Joshua was the third.
It was Joshua, that's right. Okay. And then the fourth group, I believe, was Richie. So in other words, that would be the third. Okay, and then the fifth group, who was the first? The first people that went were Will and Dan and Sharon, right? Okay, so then who am I missing? There we go. Okay. Okay, so that's the order we'll do. So probably just, based on last time, that'll be, Tuesday, that will be Thursday, but nonetheless, as before, you should send me stuff, everybody should send it to me on Tuesday, and then if you want to make updates after that, then you should let me know. But, again, the point of this is really to get you guys feedback and stuff like that, so you should be, well on your way and making good progress up until that point. Good suggestion. Other questions or suggestions or anything like that? I guess you got yourself to go first, but that's okay.
It's trying to be nice to everyone.
Yeah, there you go.
So how do you make the simulations faster?
Okay. So the question is, how do you make the simulations faster? We are actually planning to talk about that on Tuesday. So one of the most powerful ways is basically to write things in behavioral models, actually not even necessarily using Verilog A, but actually using Verilog. Okay, so when you use Verilog, the trick between Verilog and any of the other simulators is Verilog is event-driven, right? So if you do things right, it'll really only sort of make the computations when you really actually need to have something happen, right? It's not going to go through some detailed model or some detailed math or anything like that. Now, having said that, there's a bit of an art to how you really do it. So we'll talk some more about sort of how you go about doing that probably on Tuesday, or in fact, it should be on Tuesday unless something goes horribly wrong today. But that's one of the main sort of tricks to be using. The other trick to use is basically to use different, let's say, levels of accuracy or different degrees of accuracy in your behavioral model itself to try and answer different questions, right? So if you have some sim that's just really going to take a long time, then you may have some of the components be more simplified than they otherwise would have been, just to be able to run it fast enough. Yeah?
How was the channel? Because most problem comes from the channel.
So what are the issues you get from the channel itself?
It's too slow.
So how did you actually implement the channel?
We're just using the channel model.
So yeah, so if you just use the model itself, remember, at the end of the day, all you really need is essentially the set of coefficients, right? And even if you're doing clock recovery or something like that, you can basically just oversample it, not at too aggressive of a rate, and then just store essentially the, let's say, oversampled rate samples, and then just run that whole thing as a convolution. Right? Because if you think about it, when you run your channel model, if you're running that out to 100 gigahertz or something like that, you're fairly heavily oversampled relative to what you might actually need, even to get sort of a reasonable behavior out of the CDR and those other kinds of things. Does that make sense? Or
Just saying do a pulse response and then convert.
exactly, just do a pulse response. You still want to do an oversampled pulse response because you're doing the clock recovery. Now, that's not to say that what you'll get from that will be super accurate, because if you have a coarsely, oversampled pulse response, then the clock recovery won't be exactly right. But in terms of getting the functional behavior and showing that things are working, that'll actually be pretty good.
Are you saying we're just getting a pulse response in Spectre, and then everything else is in MATLAB or in other?
No, well, so you could do it that way, although I imagine that most people will do it in Verilog simply because it's easier to write the rest of the digital stuff around it in Verilog. Right? But basically, even in Verilog, you can just get something that is the pulse responses, and then just run that as a convolution on the actual data you send through it.
Oh, okay, I see.
Right? And you can write that even in digital Verilog.
Okay.
Yeah. Does that make sense now? Or?
But you're saying it just involves running this actual SPICE simulation once.
Exactly. Now, that's not to say that Verilog is infinitely fast, right? But generally speaking, if you do that, that'll speed things up quite a bit. Does that make sense? Or yeah.
Then what about the time step, since you're given like 20 ppm offset?
Okay. So apparently some people ran into an issue where in Verilog they hit the 1 femtosecond, time limit, which is apparently the minimum, time step you can actually use. If your thing works with like 50 ppm and that avoids that issue, fine, no problem, right? So if you work with more than 20 ppm, that's totally fine. The other trick you can play is just, if everything is a fully behavioral model, you can just rescale all the time constants sort of arbitrarily, right? Now, if you have something where you're doing a mixed mode simulation, then you might have a little bit more of a pain in the butt, because if it's a mixed mode where you actually have some real analog stuff, then rescaling time in the real analog is a little bit more annoying, right? But if you have a fully behavioral model, just rescale time to make it all work. Does that answer your question? Or yeah. Other questions? Or? Okay, good. Well, at least people are starting to actually put everything together. So actually, I guess, who has like some kind of sim with adaptation and clock recovery and everything else going? Okay, that's the same group. So okay, got it. Well, so again, hopefully people will be well on their way. Within the next kind of week and a half or so. People run into trouble, definitely let me know, and we'll see what we can do. Okay, so unless there's any more questions on either project or previous kind of stuff, I think we can go ahead and sort of dive back into the material for today. So last time we were basically talking about supply regulation. In particular, we started going into kind of what are going to be some of the trade-offs in terms of how you design these regulators. And in particular, one of the last things that we talked about was just that if you really go through and you sort of do a fairly detailed optimization, what you basically find out is that if you want to improve the supply rejection of your regulator, there's a pretty nasty trade-off in terms of how much power you have to spend in your feedback amplifier. Because basically what we said was that if we sort of follow the right rules in terms of the amplifier itself, so that we always make it so that the amplifier kind of maintains a certain low impedance up until the point where just naturally we get that impedance from the RC filter, then the implication of that is that if you want to get, let's say, a 2x better supply rejection, you really have to do two things in the amplifier. First, you have to increase its gain, just to knock down the DC rejection you're getting. And then second, you also have to increase its bandwidth, just to now, again, meet that new point on the RC filter curve. Okay? So the implication is that for 2x rejection, you need 4x gain bandwidth. Right? So there's a quadratic there, which is kind of nasty. So then what we started talking about was, well, okay, can we do a little bit better? And the way I sort of pointed out one particular method to do better was by showing that, look, if you really follow this optimization for actually a pretty wide range of the kind of parameters, the amplifier is not really doing much except acting as a wire. Okay, it's really just sort of trying to get the variations that are out there on the, let's say, well, okay, I don't have a picture there, but the variations that are out on the regulated supply to actually affect the VGS of the power device, right? So then what we said was, well, okay, that's kind of dumb, because if that's really all we're trying to do, why don't we just change the output stage to, instead of being a common source, actually be a source follower, okay? So we started talking about some of the practical implications of this. We'll get back into that today. But conceptually, what we basically said was that in reality, what we'd really like to be able to do is something that looks like this, right? Where our power device is this NMOS transistor here, and then we just have this feedback amplifier over here, which, maybe indeed is going to give us some additional gain. But notice that even if the amplifier itself does nothing at all, right? Even if that basically gain, for all intents and purposes, is 0, you still get the 1/GM of the source follower itself, right? So that's, again, actually quite nice, because it says that you can actually get a reasonable rejection even without any power at all in the amplifier. Right? So there's kind of like this minimum rejection you get now. Whereas before, you automatically had to spend power just to get any kind of rejection at all. Okay? So just to make sure this is sort of really clear and maybe as a brief review, I just want to do sort of a quick comparison in terms of the power supply rejection ratio for these two topologies. And again, I know there's a bunch of practical issues with actually building that source follower thing. Don't worry, we'll come back to that in 1 second. Okay? So let's compare, again, the sort of common source version. So this is, let's say, my reference. That's my regulated thing. And of course, I have some decap out over here. If I compare this common source versus the source follower, which again now just looks something like this. Okay, and then of course just, pay close attention. Obviously the signs on the feedback amplifier are flipped here, because for the common source, the gain of the output stage is negative. For the source follower, it's positive. Okay, so just don't make that mistake, because of course you'll be very unhappy. Okay? Okay, so what we basically said was that the power supply rejection ratio in this case was basically proportional to square root of the output stage gain times the kind of normalized gain bandwidth of the amplifier. Right? That's basically what we said the power supply rejection ratio for this thing would be. Okay, so now here's the kind of interesting question. What is it for the source follower with the exact same gain bandwidth from the amplifier? And let's assume that even somehow magically the gain, quote unquote, of the output device, and by gain I just mean GM times whatever the linearized resistance at that node is. Let's assume that even that is the same between the two cases. Okay? So what would the power supply rejection ratio be for the source follower?
I mean relatively, or
Say that again?
you mean relatively?
No, I mean, well, if you can do relative, that's fine, although it turns out that giving, let's say, just the answer is easier. What's it sort of proportional to? What do you guys think? And by the way, I'll give you a hint. Oh, somebody say something? Oh, no. So over here, if the gain of the amplifier is 0, how much rejection do you get? Or how much is the source follower helping you by? And remember, we're always comparing it sort of against just that natural network we had right there. So how much are we, lowering the impedance by just by having a source follower there, and even without having the feedback at all? On this picture, what's the equivalent model if you have 0 gain in the amplifier?
1 over GM.
Yeah, there's 1 over GM there, right? Now, 1 over GM has units of transconductance, which doesn't exactly tell us anything about, or it's not exactly directly rejection, right? What we really want is how much rejection we get from that, right? But okay, to get rejection, what do we have to normalize that 1 over GM by?
R not parallel.
There we go. You have to normalize it by the impedance that was there anyways, right? Which is just R out parallel R load. Well, okay, so what is GM times R naught parallel R load in these terms that I've used right here? Yeah, it's just A0, right? Okay, so that's basically telling us no matter what we do, we get A0. Okay? So now you guys tell me, is that it? Do I just get A0, or what else do I get? And how does it modify things? And again, just think about this model right here. So we've already included what this does. Now we just need to know what this piece would have done.
There's like approximately AA.
Well, sort of. So remember, I kind of want it in this form, right? So here I've already done all of the optimization I need to do to figure out what the sort of best I could do once I picked the gain, I picked the bandwidth, and all that other stuff from the amplifier. And by the way, I'll give you guys another hint. If that 1 over GM wasn't there, like this fixed thing was not here, can you tell the difference between the source follower and and the common source? You can't, right? It's identical. Okay, so what does that mean you get in terms of rejection? What should you be adding into this?
Same equation from before.
Yeah, it's the same, but the only question is, do I multiply, do I add, do I subtract, what do I do? So it is indeed the same form, but the only question is, do I get a multiplicative gain? Do I get an additive gain? Like, what do I get? By the way, so with the source follower, given that I always have the gate, I have basically the variations that happen at the regulated output. At the very least, they always have an impact of like 1 on the VGS of the output device. Right? The gain is always at least 1 to 1. So now at DC, when I add that amplifier in, how much is like the additional thing that I get from it? How much does the, beyond that gain of 1, do I multiply the gain by AA, or do I add a gain of AA on top of that in terms of the change on VGS?
Multiply.
Okay, so you have to be a little bit careful. So if this is, let's say, delta V, right? I do indeed get an AA times delta V, obviously with a minus here.
It's 1 plus A.
There we go. It's 1 plus. Okay? So that basically tells you this thing is additive too. Okay? Because what it's basically saying is that, look, this A0, you get that no matter what the bandwidth of the amplifier is. Right? Then when you start adding the amplifier in, that just adds in some extra rejection. Right? So obviously if you spend a lot of gain bandwidth, then, okay, maybe the difference between this and this isn't that big. But remember, you generally don't want to spend that much gain bandwidth. You don't want to spend that much power, so just having that plus A0 term there in the first place buys you actually quite a bit. Yeah?
I'm not sure how you got the square root plus. I mean, how do you write it directly?
Why is the square root?
Yeah.
Oh, okay, so remember that, does this make sense? The fact that if you want more PSR, like PSR, the gain bandwidth has to go with PSRR squared. So just take square root on both sides. Right? That just comes from here. Right? So if I said that gain bandwidth, or rather, I need gain bandwidth squared to get to PSRR. Right? Then I can flip it around. Right? Or sorry, actually I should do it this way. Gain bandwidth equals PSRR, or proportional to PSRR squared. Right? So that just says that PSRR is proportional to the square root of gain bandwidth. Right? That's all I did. Does that make sense? Or yeah, that's literally all it came from. I mean, there's a series of equations, obviously, that can get you to this, but literally, if you understand that this is the effect, then it's an equivalent statement. Okay? Okay, does this kind of make sense to people, or? Okay, so now if that makes sense, then as we started talking about last time, there's unfortunately some quote-unquote practical issues with this, right? So the first one that we pointed out was that, well, hey, wait a minute. I mean, if I just throw an NMOS right here, and I said that I want this thing to be a low dropout regulator, meaning that I want this voltage down there to be close to the supply voltage, then I kind of have a problem, right? Because in particular, as we pointed out, if I just use VDD here at the drain of that source follower, and then let's say that I want that output to be at VDD minus V star, because again, I want it to be sort of an equivalent dropout comparable to the common source regulator. And that automatically means you need something like VDD plus VTH at the gate of that transistor there, right? And okay, now obviously we kind of have a problem because VDD plus VTH is larger than VDD, and so that's outside of the supply rail, right? Okay, so that is indeed a real problem, but basically there's a couple of things you can do to try and fix it, okay? So the first is perhaps the obvious, slightly brute force solution, which is just say, okay, well, I obviously need a higher supply voltage, but the good news is I don't need that like everywhere. I really just need it kind of on that gate right there. So if I magically have a higher supply voltage to begin with, like, from whatever reason something else in your chip needed that higher supply, then in principle you could just take that higher supply voltage, connect it to the amplifier you use to drive that NMOS transistor, and then you're kind of okay as long as, obviously this amplifier has enough headroom and things like that. Okay? Turns out there's actually some other issues related to this. We'll talk about that in 1 second. But in principle, this does work, right? And this tends to work out nicely only because a lot of times when you do this, because of this effect, you basically say, okay, look, I really don't want much gain bandwidth. I'm just relying on the natural rejection of the source follower anyways. So the fact that I use an extra higher supply on the amplifier, if I'm not burning much current there anyways, maybe doesn't matter that much. Okay? The other way you can do things, which is again actually relatively common, is maybe you indeed do not have that extra power supply hanging around. Well, in that case, basically you do something to sort of generate it, right? So you basically take some analog voltage or some other type of voltage and you just boost it up to get to whatever the voltage you need for that real source follower is. Okay? I won't say too much about exactly how you do this boost, because it turns out there's lots of different circuits you can do to build that. But if people are interested, just come bug me. I can tell you some more about it. But typically speaking, it looks like some sort of switch capacitor kind of circuit where you charge it to VDD at first, and then you boot the bottom of it up to get above the supply rail. Is there a question? Or?
But if you try to do switch cap, doesn't it turns this whole thing become like a switch cap regulator instead of linear regulator?
It's still a linear regulator because I'm only using that switch cap to generate a higher voltage at the gate of this thing. Right? So I'm not actually supplying real current off of it. I'm just trying to use that to control the gate voltage of this transistor here. Does that make sense? Or? Okay, make sense to people? Or? By the way, there is one other thing that you can sometimes do if the technology gives you the model for it. So if you get a native transistor, meaning something that basically has 0 threshold voltage, then that's another sort of halfway reasonable way of doing things. Right? Because then at least if the threshold is 0, well, okay, roughly speaking, that gate's at VDD, and you can kind of almost get things to work. Okay? There's a little bit of a minor problem in that, building a real rail-to-rail amplifier is a pain in the butt, but actually, as I'll explain in 1 second, probably you'll do things not with really analog, but actually in a somewhat more digital way to make that a little bit easier. And again, I'll explain what I mean by that in 1 second. Okay, so that's kind of practical issue number 1. Turns out there's another very significant issue you have to be pretty careful about, actually not just in the source follower, but even in the common source, which I'm just going to say a little bit about here. Okay, so let's say that indeed I take that source follower, and I'm really just using that thing to try and get that native rejection of the source follower itself. Okay? Well, okay, so when we said that we're getting good rejection from that thing, what we were really saying was that, well, okay, if Vreg moves around, if the output from that thing moves around, what we were basically assuming was that the gate stays totally pinned, right? So that if that output moves around, the VGS automatically changes, right? But guess what? Unfortunately, there's a CGS right there, right? In fact, not only that, there's also, and let me just extend this up, there's also a CGD right here, right? So in fact, if I just drove this with some, let's say, relatively high impedance there, then what's going to happen is that both the supply voltage directly and the regulated output are basically going to couple back onto that gate, right? So if both of those couple back onto that gate, well, now actually if the gate is moving along with the regulated output, guess what? You're actually not getting any GM at all, right? In fact, even worse, if the supply couples back onto here, now actually the thing could be amplifying the supply noise, right? Because you're sort of moving this gate. Now the source follower is like trying to track the supply voltage, right? So it turns out when you really do this, what you always end up needing to do is ensuring that there's some amount of basically fixed cap right here. Okay, so as an example, if this is like the resistance of the amplifier, and this is sort of the, let's say, the voltage source you're using to generate that thing, you almost always end up having some amount, or trying to guarantee some amount of fixed capacitance there, relative to the capacitance of the sort of source follower itself. Because basically, if you don't have enough capacitance there, then at high frequencies, the whole thing just starts to look sort of like an open circuit, or certainly much higher impedance than you would have liked to have. Okay? Does this kind of make sense to people, or? Yeah.
So by doing this, do you move the dominant pole back to the gate.
Ah, okay. So indeed, for exactly this reason, it's very, very common that when you build these source follower things, you basically say, okay, look, I got this A0 of rejection. And getting more than that is a pain in the ass, because I kind of need that big gate cap there just to make sure I really get the A0. I have to spend power to get more than that. So a lot of times the solution you end up with when you do this is you just say, look, I'm just going to get that A0 and be happy with it, right? And what's kind of nice about that is that if you indeed do that, that actually solves a lot of, or allows you to solve a lot of the practical issues in a fairly straightforward way. Because basically now all you're really trying to do is just get that DC voltage right. Now you're really not trying to go after really fast transients or get a super high bandwidth feedback path or anything like that. You're just trying to get that DC voltage to be right. Okay? What's nice about that is that now you can actually play a lot of you can actually do things that would traditionally be kind of dirty or a little bit annoying, and they'll actually work just fine. Okay? So as an example, as we were saying before, even if I had like a native NMOS device there, I'd still want to get this voltage up somewhere close to the real power supply, right? And building an analog amplifier that does that, and then, by the way, having that analog amplifier not have a horrible output resistance relative to VDD, meaning that if you move the VDD, the output will just change directly, is pretty tough. Okay? But one thing that is pretty easy to do is you just replace the amplifier with basically a comparator. Okay? You take that comparator, you feed it, at least conceptually, into some accumulator. And then you feed that, again, conceptually into some DAC. And then you just feed that into the gate of that transistor there. And then, oh, by the way, you can basically throw as much cap at that gate as you want. Because again, all you're really trying to do is keep that thing DC-wise relatively fixed, right? And so, of course, this would be the rest of the feedback loop. Okay? In fact, in some senses, you can do things that are even easier than that. Because you don't even really need like an accumulator in the digital domain. Because, I mean, okay, you can put it there, but it's not even actually required. You can kind of actually merge these two functions here by basically just taking that output of the comparator and pretty much low-pass filtering it. Okay, just doing something like that. Okay, because notice that if I low-pass filter it, okay, the comparator at least conceptually sort of already has quote-unquote infinite gain. Right? Because basically if you see any average offset, then it'll always keep giving you 1, 1, 1, 1, 1. Right? So then this RC filter, that would just sort of try and knock off all of the sort of switching or the dithering around once you get to the lock point. Right? And now notice what's nice about this, because of where I've put the cap, I really am referenced to ground. Right? And I don't have to worry about, amplifier jumping around and other things like that. Okay?
So the way the comparator approach is just a way to create a DC bias.
Exactly.
Okay.
Exactly. Now you could build the comparator to try and really go after the higher speed things, but pretty typically when you do this, and oh, by the way, I should also mention that when you're doing that boost, since it also tends to be like a switch cap kind of circuit, having the clocked comparator thing is also kind of convenient in that everything now just becomes clocked by the same things. Okay. So by the way, this was, I think, originally basically either explained or proposed by Den Beston in JSSC, and this was in 1998. And yeah.
I got a question for this thing. So basically, right now you actually introduce a clock into your feedback system. So it really depends on how strong this low-pass filter is. Chances are you're probably not going to knock this thing down entirely. So you're going to see
true.
some pulses at the outputs. Do you actually care about that?
Say that again?
So you're probably going to see some clock feed through all the way to the outputs.
It may not be clocked feed through. You will probably still see some dither from the comparator. But the good news is, really the only thing that sort of stops you from making this kind of as low as you want is either just physical size or perhaps leakage in sort of, the transistors themselves or in the capacitors. But by the way, since you tend to clock this, you'll also tend to build this in a switch cap kind of way, right? And in fact, I mean, you'll still want some continuous filtering just to sort of knock off, let's say, the glitches and stuff like that. But actually, the whole thing tends to actually work out pretty cleanly once you've sort of introduced that clock. I'm not saying it's, let's say, the easiest thing in the world, but actually you can get very, very low ripples there. Because again, you can build extraordinarily high time constants with a switch cap. Yeah?
Do you mind on like a ballpark summation in terms of how much suppression you actually have on this?
Oh, easily in the 50 or 60 dB, somewhere in that ballpark. Probably, maybe I'm a little bit aggressive, but 50 dB should be very doable. Yeah. I don't know, anybody who did this recently want to comment? Yeah, 50, 60 dB, basically sub 1 millivolt. Yeah, actually, maybe I wasn't too aggressive, easily sub 1 millivolt. That's very doable. Yeah. Other questions? Or? Yeah.
So it looks like the first block diagram is still a little bit different from the second one, right? Because the first one is still
When you say you mean this versus
the
this?
right-hand side, yes. The upper one is different because
You are
kinda
right
still
that they
have-
are slightly different in the sense that I'm putting an additional, let's say, digital gain or a digital, let's say, an analog integration here. Whereas here, this integration, obviously, it's only, I shouldn't really call it an integration, it's just a low-pass filter. But what I'm relying on here is that the comparator, if I really had no noise in the system, the comparator effectively has infinite gain anyways, right? That's kind of what I'm relying on. You're right, technically, these aren't exactly identical.
I guess what I'm saying is you have an extra pole at 0 for the upper one, right?
Extra pole in this one?
Yes.
Well, okay, not exactly. So technically, both of these would be, well, at least in the feed-forward path, both of these would have one pole. It's just that this pole is at basically 0, and this pole is at wherever I've defined that by the RC filter.
But you also have another pole after the deck, right?
Oh, I see. You're saying because I added this cap. Okay, fair. That's right. That's right. Although once I've put a pole at DC, then maybe that doesn't matter so much. But yes, okay. You are right. Yeah. Other questions on this? Or? Okay, so as I mentioned, this is actually a pretty typical thing to do. If you actually check out this reference, which is now about 13 years ago, they actually talked about a lot of this stuff. They basically built it pretty much this way, just with a booster. Took, I think, people some time to realize that this is actually sort of the right way to do it, but it's actually fairly common these days as well. Okay. Now, as I mentioned earlier, I started talking about these issues of like referencing the gate in the right place and stuff like that. I brought it up in this context of the source follower, but turns out even if you were doing the normal common source design, just because let's say you don't want to deal with this extra complexity, or for other reasons you sort of have to do it that way, you'll actually have very, very similar issues. Okay. So let's just take a sort of quick look at that as well. So let's again just sort of draw our normal common source regulator. Okay, let's say it looks basically like this. Of course, we've got our decap out there. We've got our load. Okay, so if you remember when we were talking about it last time when I drew those sort of small signal models, I was always assuming that this VBP here was basically perfectly correctly coupled to the power supply voltage, right? Because notice what you really want is that if the power supply voltage changes, you don't want that VGS to actually change, at least not because of the fact that the supply changed directly. You only want it to be changed because of the action of the amplifier, right? So that basically means that, okay, we better be careful because once again, hey, you're always going to have cap, for example, from the CGS of the transistor, as well as, more importantly, from the CGD of the transistor, okay? So it turns out in this context, the CGS is actually kind of good, because notice you want this VBP to really be coupled to VDD, but the CGD is bad, right? And in fact, any other fixed cap that's sitting there is also bad, okay? So what really happens is if you get something like this, and by the way, it's kind of unavoidable, at least at some frequency, what's really going to happen is that the effective GM you get is not going to be as high as you thought it was, right? Because basically, just due to the fact that there's coupling onto that gate, the GM is going to sort of act like an extra or a lower RO, right? So just maybe to draw this as a small signal model. Right, if when I yank on that power supply there, the VBP also has some coupling onto it, right? Let's say something that looks like this. Then basically what we're essentially saying is that some fraction of that GM unfortunately yanks some extra current out of the output as well, right? Okay, so again, this is actually something you have to be pretty careful about, because if you don't sort of pay attention to this, then again, you can actually get some pretty bad results, okay? So what this is basically saying is that, you really have to pay very close attention to how you've referenced that VBP there. So as an example, if you have to like route that wire from the amplifier, better make sure you shield it with VDD, not with ground, right? Because if you shield it with ground or if you put anything that's related to ground, you'll get worse rejection, okay? Now, I've kind of talked about this mostly as a capacitive coupling issue so far, But actually, this is even an issue basically at DC, right? Because if you think about sort of, you've always got output resistors and things like that. Well, even if those are not exactly right, or too large, or ratioed the wrong way, again, you'll have a problem. Okay, so let's actually just sort of draw a picture of that. Okay, so if you guys remember, I said that the typical way you'll build this is with just some very simple, current mirror loaded kind of amplifier. Let's actually go ahead and draw that. Okay, so let's say that's our load right there. This is basically our amplifier. It looks something like that. And for reasons that will become clear in 1 second, I'll draw this as Vref here and Vreg there. Okay, and then I take this output and I feed that to that power transistor right there. Okay? And of course, this right here is also Vreg. Okay? Now, by the way, I have this bias down here. Let me just, for now, draw this as some V bias. But as we'll see in 1 second, there may be actually something pretty clever that we're going to want to do to actually really make the rejection of this thing work out. Okay? Okay, so now, what happens when you yank on the power supply relative to ground? What happens to this VBP node here? What does it do? And I don't need the exact answer, just conceptually, what are the things that you need to pay attention to? So, and by the way, don't even worry about the feedback right now. Open loop. If you yank on this power supply, what is that output going to do?
Up a little.
Say that again?
Go up a little.
Okay, so, by the way, what do you want? So if I yank on this power supply, VDD, by 10 millivolts, if you had like the ideal response, open loop, what would you want the amplifier to do? How much would you want it to move and in which direction?
Go up by 10 millivolts.
Yeah, you'd want it to also go up by exactly 10 millivolts, right? Okay, so is that amplifier going to do that? Okay, I see some people shaking their head. Why not? What's stopping it from doing exactly that? By the way, maybe we'll ask one thing. Will it go up or will it go down with the power supply? Like, is the direction at least right? And again, open loop right now. So just assume this is some, magic voltage that's completely separated from the regulator for now. We'll fix that in 1 second. So open loop, what does that amplifier do? Yeah, it will go up, right? Now the question is, does it go up most of the way, or only a little bit, or what do you guys think?
Partially. Go up partially.
It does go up partially, but let's say if you were back in 140 and I just gave this to you as the first thing you saw, and I told you that this was a current source down here, and everything was magically perfect transistors, so those infinite ROs. How much, when you say partially, like how close to partially, is that like only a little bit? Is that like all the way? Like what do we mean here? And let's do the simple case. Let's assume everything looks like perfect, infinite RO transistors.
It should go perfect.
Nothing.
Oh, you didn't say anything?
Well, I say that if everything's ideal, you don't see the voltage going up.
Ah, are you sure about that?
No, it should
Yeah, the
go
ratio
up by
of the
perfect
resistance.
amount.
Yeah, it should be perfect, right? Because notice there's a diode right here, right? If you yank on VDD, then that thing should also yank right up, okay? And if everything was perfect, then this mirror device should do the exact same thing and also yank this guy up perfectly, okay? Now the bad news is it's not 140, in fact, and it's not also the 1950s or whatever it was. Everything has RO, right? Not only that, like there may be some, you don't have finite gain in everything, right? So in reality, this isn't exactly going to track, right? In fact, what's actually going to happen is that VBP will only go up some partial distance of the way. Now, what are some things you can do to try and make sure that it goes as much as you can possibly make it? Like what's one straightforward thing that you can do that will help it from a design standpoint?
Let's go with that guy.
Which guy?
The input devices, you want to have a high input impedance. I mean output impedance.
There we go. So you're absolutely right. So what you really want to make sure is you want to make sure that this output impedance here, so basically the RO of those NMOS devices, is much greater than the 1 over GM of those PMOS devices. That's absolutely correct. Okay? And indeed, when you build these things, better, you should really design it that way. Now, Unfortunately, cascode is often hard to fit into this thing. Just if you work out, the VGSs on everything, the cascodes usually are tough to do. But that does mean that typically these will be long channel devices, whereas, as we'll describe in 1 second, these are going to be short channel devices for actually a very good reason. Okay? So now, it turns out there's actually one other very clever thing that you can do, which turns out to help with some of this issue, or at least from a DC standpoint, make sure that you've sort of done things right. Okay? So if you kind of pay attention to this, like exactly where this lands right here is really sort of being set by this arbitrary bias that I fed into this thing in the first place. Right? Because at DC, if you move the supply around, you have to work out all the different ROs and the VDSs and what exactly that does to figure out where exactly this bias should be sitting. But that's not really what you want, right? What you really want is, once you've closed, in fact, even without the loop being closed, you want it so that this voltage here should really be giving you exactly whatever the voltage should be to get the right current into that load, right? That's really what you'd like to have, even without the amplifier doing anything, right? Because all the amplifier can do is apply some gain and get it close to that point. But if you had an error to begin with, then you always have to work against that error, right? Well, it turns out there's actually one really clever thing you can do to make it so that the amplifier naturally biases to exactly the condition that I just stated. Okay? So at first this is going to look a little bit, let's say, like one of those things that we always tell you not to do. But trust me, it actually works quite nicely. Okay? So what I'm going to do is the following. So let's say that I have m legs for that output device. Okay, so I'm just going to assume that I have some unit cell PMOS device size now. Okay? And let's say that there's m of those unit cells for that output device. Well, I'm going to take one of those unit cells and basically mirror that current over. Okay? Well, once I mirror that current over, and I'll draw sort of the full thing so that it's clear why I did it in 1 second. Okay, so basically all I did here was just sort of build something that looks like it's kind of like a cascoded mirror, but really this whole piece right here is just meant to be a copy of this part of the amplifier. Right, so this is like the current source transistor. This thing is just mimicking the input device. Okay? So I take that, and I actually use that to generate that V bias right there. Okay? And just to make sure it's clear, if this has one leg, this transistor here will have two legs. So that now if I use one leg there and one leg there, now actually everything should line up. Everything should match up, right? Because basically, if you kind of work it out, if I have an I load flowing right here, right? Well, I mirrored it over here. So if everything was right, I should have I load over M right there, right? Then that means that I should have essentially right here 2 I load over M, right? So that in each one of the individual legs, I have I load over M, right? So in other words, what I'm really trying to do is by adding this kind of funky looking thing that may even look like positive feedback to begin with, which by the way, it does have some positive feedback in it. By adding that in, if I then match all of these PMOS transistors to each other, I'm ensuring that the current densities for all of them are the same. And if I've ensured that the current densities are all the same, then now, at least from a, let's say, if I've really done that right, then naturally this amplifier should bias itself to whatever bias voltage you need here to get the right current at that output. Okay? Does this sort of make sense to people, or? Okay, now, turns out there are a couple of things you have to be a bit careful about here. So, what are some things that you think, might be a little bit nasty, or that you have to be careful about? Yeah?
Stability of the positive feedback loop, you actually need to cue the loop gain property at the current source.
Okay, so that's actually a great question. It turns out that once you connect this VReg right here, it's actually pretty tough to get this thing to be unstable. Okay? And the reason is that, largely speaking, what this loop is kind of doing is it's mostly a so-called, let's say, common mode kind of loop. Now, that common mode does get translated into something you measure at the output. But remember, the main amplifier is tying a negative feedback loop to try and keep the impedance that you see over here also pretty low. Because again, if you sort of think about it, this loop that's happening here, it's sort of just adjusting the bias point of these two transistors. But if all I'm doing is adjusting that bias point, the only way I can measure that effect is by tweaking this point right here, right? But hey, I've got that negative feedback loop that's trying to force that point to be correct, okay? So you're absolutely right, you have to be careful to check that, but it actually turns out to be pretty hard to make that constraint not be satisfied. It's a great, let's say, it's certainly the first thing that you should think about. Anything else that might be a bit tricky about this?
Do you need a startup circuit?
Ah, there we go. Yeah. So you have to be careful. You have to put a startup circuit into it, right? Because you could just get really unlucky, and you have no gate bias voltage there, and this is all off, and it just doesn't ever start. So what typically people will do is indeed add some little, kick start transistor, right? And by the way, sometimes people are lazy, like me, and they'll just even tie that to ground. They'll just make it so that it's a really small current, just to make sure the thing starts, and then afterwards it basically doesn't really matter that much. Okay? But by the way, the other thing indeed that you have to be sort of careful about is that, as is sort of implied, all those PMOSs should have the same V star. Right? In other words, they should all be matched to each other. Right? Because obviously if you're not matching those things, if you're not keeping the current densities constant, then even though I tried to play this positive feedback loop trick, now I'm matching apples and oranges. Right? So when you really typically look at these kinds of things, what you should see is this big stripe of PMOS devices. You're just picking off different PMOS devices to use for different parts of that regulator. Yeah?
I do have an additional question about this startup circuitry. So do you actually care about this thing called inrush current at all?
Okay, so we haven't done anything specifically here. When you say inrush current, you mean that if you start a circuit and then all of a sudden it dumps a lot of current into the load. Okay, fair. I haven't done anything specifically here. Although, usually when, let's say the supply is ramping up anyways, what's going to happen with something like this is the real question is what's happening to the reference, right? Because if the reference is tracking up along with the supply, then nothing really will all of a sudden start because of that, right? The question then is if the reference then has a kick on it, then you might actually kick current through that supply.
Not really, because you actually have this external bypass cap. You actually need to charge up that cap. So
sure, but remember that it's all a question of how fast is that supply relative to the slew rate of this thing, right? Because if the supply is slewing relatively slow compared to this, then it's all the same.
Sorry, what?
If the supply is slewing relatively slowly and the reference is also moving relatively slowly,
Right.
then the question is just what's slower? Is it the supply ramp or the slew rate of that output stage right there?
So you actually need to make sure like your supply should run slower than this.
Well, that's under the assumption that inrush current actually matters for anything, and that depends on how you're using it actually, right? Because by the way, if remember, typically if you're doing something like this, it's on like the VCO, right? So like, okay, there's a milliamp, 2 milliamps, maybe 10 milliamps if you have a really clean VCO. If you've got a 1 amp chip next to you that could be doing much worse things than this, that may not matter that much. Right, but it's it's something that you may have to think about in some contexts.
But how would you actually make sure like the slew rate is actually all right? Because this whole thing just starting up and then.
What's setting the slew rate of your supply?
I'm actually talking about the slew rate of your circuit rather than the slew
Yeah,
rate
but
of the
remember, the only reason, so why do you think that there's going to be a big slew rate on here? Right, the only time you should really have a big slew on there is if the supply is slewing in the first place, right? Because otherwise, well, okay, maybe there's some other applications, but at least in the context of links, generally speaking, you're not going to be moving that supply around very fast, right? If it's your VCO, you're going to be trying to keep that basically as steady as you can possibly make it, right? Even if it's like your comparator or something, same. Your goal is really to keep it as steady as you can possibly make it, right? Does that make sense? Or? Okay, good. Other questions on this? Or? Yeah.
I guess I'm confused with this. So you started off by saying that when you ramp up the supply, the gate node of that PMOS should track along with it.
Mm-hmm.
So how does this loop sort of fix that? Can you just walk through it?
So all this loop is really doing is if I break this connection here and I just have some static fixed bias, right? There's nothing really setting that gate voltage there, and let's do everything open loop, right? So if I break this loop and I break the feedback loop, right? Then if I move this supply right here, the only thing setting this bias point right there is basically sort of
The ratio of the resistance.
well, the ratio of these two and some ROs,
Right.
right? So, but nothing is really, like, basically this current density in these two devices is set then purely by this bias current source, right? So when I take that output and I feed it to here, if this current density is not the right current density for that actual load at the output, I'm going to get a deterministic error, right? Simply because open loop, I've created a new voltage here that is not the right voltage for that current density here. So all I'm doing by adding this loop back in is enforcing that the current density through these two devices is the same as the current density through the output. So that even if quote-unquote open loop, and by open loop now I mean I have this connection, but I don't have this. I don't have the vreg feedback, right? Now if I keep the current densities all the same, then now what should happen is that if I move the supply, everything will readjust to keep that same current density. Is that more clear now? Or?
But you still have the VDS difference, right?
Yeah, so it's not that this is perfect, right? There's still indeed going to be a VDS difference. I guess if I really wanted to be aggressive, I could tie like some op amp or something here that was keeping the VDS of those two the same. Even if I do that, obviously there's some finite RO here, so it's not perfect. But it's a heck of a lot better than just having a fixed current bias. Is that more clear now? Great. Other questions on this? Okay, great. So the last thing that I do want to mention is, so we looked at this first follower thing, right? We said that, that was kind of nice because, it kind of got us this minimum rejection. But we said that in some cases that may not actually be a practical thing to do, or maybe it's just too complicated because, again, you get into all these gate boosting and things like this. So it turns out still a lot of places people will use these common source kind of regulators, okay? But the other thing that we saw with those common source regulators was that unless we were burning a lot of power in this feedback amplifier here, usually the gain we ended up with was too high, right? Like when we did the optimization, we usually wanted a pretty low gain, but a high bandwidth, right? So the question is, well, okay, so if we have to use this common source thing, is there some way to make it at least get the sort of the optimal design that we wanted in the first place? So at least conceptually, the answer is yes, right? Because if I can always, at least in principle, take an amplifier that has too much gain, but not enough bandwidth, and just tie it into its own negative feedback loop to actually get higher gain, but lower bandwidth, right? At least, again, in principle, that shouldn't cost me any power. Now, if you sort of see this diagram that I've drawn here that's kind of doing that, turns out that's a little bit of a pain in the butt to actually build. But I'm actually bringing this up because it turns out if you use this, if you play this, you actually do this local negative feedback here, if you do it in a kind of a clever way, which I'll show in 1 second, you can actually break that basically gain bandwidth versus PSRR trade-off. Or at least you can do much, much better than we were able to do with sort of a standard design. Okay? So to sort of see how that looks, let's actually go ahead and move to the next set of slides. Okay, so what we're really now looking at is, we said that, okay, we're going to use this local negative feedback thing to just make it so that the amplifier, at least looks more like what we want it to be, meaning that it has low gain but high bandwidth. Well, it turns out all I have to do is actually be a little bit clever with how I build this local negative feedback loop. Because just as an example, imagine that instead of just having that local negative feedback loop, not only do I use it to sort of extend the bandwidth of the amplifier, but imagine that I just shoved in some indication of the supply noise into that local negative feedback loop. Okay? And not only do I shove it into here, but actually I do something even more aggressive. I try and make it so that whatever the supply noise is, it shows up completely unfiltered into that point right there. Okay, so in fact, I don't even try and look at what happens out here. I just try and get a raw indication of how much variation there is on the supply voltage. Okay? Turns out if you do that, what you're basically saying is that, hey, if I take that raw supply noise signal and I shove it back into this amplifier, well, for some frequency range of interest, I'm actually going to be getting more feedback signal than I would have from actually trying to take this feedback right here. Okay? So I'll walk through the sort of the detail of how this happens, but in this context, you should sort of think about, anytime you get a bigger feedback signal, that's kind of like saying you have more gain in the feedback path. Okay? And hey, guess what? More gain is actually a good thing, because that means that you can correct better. Okay? So I know that at this point this sort of sounds kind of weird and like, I'm breaking some rules or something like that, but don't worry. I'll show you exactly how we make this actually work in 1 second. Okay? So let's actually look at this in sort of a little bit more detail. Okay? So conceptually, again, all I'm really trying to do is tie the amplifier into some local negative feedback, but I want to do it in a way that actually gives me a sort of nice indication of what the supply noise really is. Okay? So conceptually, it turns out it's actually pretty easy to do that. So this is like my main output device. This is like this is where I really actually want my output to be, right? So if I kind of look at this, this is what my load was, this is what my decoupling cap, this was my output device. Well, now if I want to tie this amplifier into some local negative feedback, imagine that the way I did that is I take another dummy output device, I use that to drive some quote-unquote replica load. So this replica load really just means that it's something that matches the IV characteristics of the real load. Okay? So now if I do that, then I take that and I use that to actually use that to feed back into the amplifier. Okay? So first, is it sort of clear how I've done like a local negative feedback period from drawing this picture here? And don't worry about how I build this plus over here. We'll come back and fix that in 1 second. At least, does this piece make sense? Okay, so there's really sort of two, let's say, important points to notice from this. So the first is that usually when I draw this, people say, well, wait a minute, what the hell? You just replicated the entire load you were driving. Right? So if I used to have like a VCO there, now you have 2 VCOs, didn't you just double your power? So why do I not necessarily have to double my power?
You can scale it down.
Yeah, exactly. All I have to do is, as long as I can get the shape right, I can scale this replica relative to the real load. Right? So that's indeed why I drew this as being some width divided by m over here. Okay? And practically speaking, usually you can get like a 10-to-1 kind of ratio there. Okay? So indeed, that's good. But now notice there's actually one other sort of very important thing. What's very different about this node versus that node?
The noise is different.
Okay, the
Because
noise
on
is
the
different.
device-
Why is the noise different?
Because the device is scaled by m. So
No big cap.
No, okay, because by the way, remember, if I scale the device, all the impedances, everything just scales the same way. So the resistive divider didn't change.
no, but you're scaling the circuit down by.
Right, so if the GM and the RO of this scaled by, let's say, a factor of 10 higher, and the R load of this also is a factor of 10 higher, then the SVDD we talked about last time is identical, right? Because that's just a resistive divider, right?
Yeah, but the actual value of the noise will be different. I mean, the supply is fine, but the actual.
Right, but when you say noise, what you're measuring is the variation of that point right there, right?
Yeah, I mean the supply noise is the same, but the device noise will be different, right?
Oh, I see. You're absolutely right. The device noise will be different, but remember, I'm dealing with 100 millivolt supply noise. So I'm not even sure I'd have to calculate that once, but you need a really small device before that even comes into the picture, right? But you are right, the device noise is higher. The bigger issue in this context, because, by the way, for most links that I've worked on, supply was always the dominant thing, at least in terms of jitter and stuff like that, but you are right. So the bigger issue, or the bigger point, is actually what Matt said, which is, look, there's no decap here, right? Why is that actually kind of nice? By the way, it's nice for 2 reasons. The first reason is actually kind of silly, but is important. So if I had to put a big decap here, would I want to do this from an area standpoint? No, I wouldn't want to do that, right? But okay, good news, I don't actually need any extra decap there. And in fact, you don't want it, okay? Because it turns out that by not having the decap there, I'm actually going to be able to do better than I was able to do before. Okay, and so here's the way that works. So let's just compare the variations you see on this replica point relative to the variations you see on this regulated point. And just open loop. Okay? Fook, you mind closing the door maybe? Thanks. Okay, so I'm just drawing that section of the whole regulator now. And let's even again just do this completely open loop, right? Okay, so on this main thing right here, remember we said we just had some RC filter, right? So we had the resistive divider between the output resistance of this and the load, and then filtered by that decap, right? So if I draw that transfer function versus frequency, I get something like this blue curve here, right? Well, hey, on this replica node right here, I didn't put any decap at all. Right, so now that means that, okay, there's always some parasitic cap there, but hey, that means the bandwidth of that replica node is much, much higher, right? Well, if you think about it, that means that when I put variations on this power supply here, beyond whatever the bandwidth of this node is, I'll start actually seeing a larger magnitude on this replica than I do on the real thing, right? In other words, if I look at the ratio of the supply noise signal here on vrep to the supply noise signal there on vreg, I get some transfer function that looks like this, right? I kind of get this high-pass filter looking kind of thing, right? Why is that actually really good? Why is that actually really nice?
Kind of extend your bandwidth.
Okay, you can think of it that way, but let's maybe flip it the other way. So if I told you that my bandwidth that I had available to me to measure that supply noise signal was up to this point here, what benefit did I get in terms of measuring the supply noise at that frequency?
Effectively more gain.
Yeah, it's effectively more gain, right? That's pretty cool, right? Because by the way, let's say I double the bandwidth. How much more gain do I get? Assuming it's all first order stuff, which in this case it is. Yeah, you also get double the gain, right? Okay, so this is maybe skipping ahead, by a little bit, but what does that mean about our power supply rejection and how it's going to change in terms of how much power we need in the amplifier?
Makes it constant, right?
Not quite.
We don't have the square
2x
root
only, not
anymore.
4x.
Yeah, you don't need the square anymore, right? So now what's going to happen is, because of this effect, right, if I'm getting extra gain just from the fact that I have more noise signal here to begin with, that means that I don't have to do both things anymore, right? All I have to do is if I increase the bandwidth, automatically I get extra gain. Okay, so indeed, my power supply rejection ratio is now going to be linearly related to the bandwidth, rather than through that quadratic. Okay? So indeed, that's actually why this is really nice. Okay? Now, by the way, there's going to be a picture exactly showing this thing, so you don't have to write, frantically too much right now. But there's actually one other thing that I want to sort of point out, which is we've just convinced ourselves that if I look at this if I look at this replica point right here, I would actually be getting extra gain. Okay? But in this picture that I've kind of drawn right here, I'm still sort of showing feedback both from that replica and from the real output. But hey, if I always get more gain from here, how do you think you really want to build the regulator? What's like the best power supply rejection you can possibly get?
Don't have the other one.
Yeah, don't have the other one at all, right? Just look at this, because hey, that gives you the best supply noise signal you can possibly get. So indeed, turns out, if you really want, let's say, the best supply rejection you can get, the best you can do is indeed to build what's called a replica biased regulator. Okay? And the reason it's called replica biased is that, as we've just sort of explained, or we've just, let's say, at least in words said, in this case, I really am not going to have any feedback whatsoever from the actual load. Okay? I'm only going to take the feedback from the replica. And again, the reason I've done that is that from the standpoint of power supply rejection, this is the best point for me to measure that supply noise signal, because it has the most gain on it. Yeah?
But what happens there's mismatch between your between the low and your replicate?
Ah, okay, great question. So that's one of the first questions people usually ask, which is, well, what happens if there's mismatch between these two? What if it's not exactly right? Okay, so turns out there's lots of different things you can do to fix exactly that issue. Now, we'll talk about this a little bit more in this lecture as well, but first of all, if this was in the context, for example, of a phase lock loop, where this Vref is coming from the charge pump, do you care? No, you don't care, right? Because at the end of the day, the phase lock loop is going to force this voltage to be whatever it's supposed to be anyways, right? Now, even if you're not in a phase lock loop, remember, we're really doing this because what's happening is that at high frequencies, we get that extra gain. That does not preclude us from measuring if there's a DC error and fixing it through some other means, right? So an example, you can imagine I can measure if there's an error between these 2 points, and then tweak this Vref until I fix that error, right? Now, by the way, keep that in mind, because I'll use that to solve one other problem with which people usually complain about with this particular structure. But just, remind me, or, you'll see it maybe in like 2 more slides. Okay, but it's a great question. That does indeed mean there will be offset between them, but trust me, there's lots of things you can do to fix it. Okay? Okay, so this is just saying sort of what we said before. I think people hopefully get this. The point here is that now, if indeed you get that extra supply, boost in the signal on that replica path, then now, nicely enough, you only have to increase the bandwidth of that amplifier, right? Because just by increasing that bandwidth, you'll automatically get the extra gain from that replica path. Okay? Now, okay, we have to be a little bit careful. Obviously, eventually that replica path will run out of bandwidth too, and then you won't get any more gain. But that just really means that when you design this thing, you make sure that you maximize the bandwidth on that node. Right? So you try and minimize all the parasitics. You try and keep things as fast as you possibly can there. Okay? Does this make sense to people, or? Okay, great. So, again, this is a pretty nice benefit, because obviously if you're shooting for that extra factor of 10 in supply rejection, you just saved yourself a factor of 10 in power in the amplifier, right? So, indeed, pretty big deal. Okay? And so, by the way, just to give you some sort of rough numbers, if you do this, you can pretty easily get sort of 30 to maybe even 40 dB of rejection with minimal power in that feedback amplifier, with maybe something like sub 10% of the load current in that amplifier. Probably typically like 5-ish% or so. Okay? Now, obviously, that depends on exactly how much decap you've used and things like that. Obviously, the more decap you use, the better it is. But pretty effective technique, because you can indeed build some very, very efficient regulator structures and still get very, very high rejections out of them. Okay? Now, there's one more thing that people usually sort of complain about when they do this, or when I first show this, I should say. So you complained about mismatch. That's a very, very valid question. Is there anything else related to maybe mismatch that, yeah?
Depends on where you actually detect the output voltage, because most of the time people actually prefer to tap the output voltage right at the outputs, because you actually have all the routing resistance. Right now you're actually not tapping at the outputs, so probably you're actually not regulating it at the right place.
Okay, so you said that, if I'm not careful about this, there's actually some resistors and things here, right, that, maybe I'm not getting it exactly right. That's fair, although that issue, I think, is existing in any case. But you are right. I'm not directly looking at the output voltage. And so I'm sort of, quote-unquote, open loop, at least if I just draw this by itself. I'm sort of relying on open loop that being kind of okay. That's fair. But there's, let's say, a very practical thing here, which usually people complain about. Oh, it's not practical? Okay, well. If I forced you to build this, what would you do?
It's too hard to replicate the load.
What was that?
It's too difficult to replicate the load.
Ah, okay. So you said it's really, how the hell do I replicate the load, right? Okay, yeah, no. So obviously you don't want to do that, right? You don't want to take your whole chip and copy the chip and multiply your whole chip power by 2. That's obviously bad, right? Turns out, for many loads, you can actually build a very simple replica. So in particular, by the way, for supply regulated, for ring oscillators, turns out, and you can, look at some simple math that shows this. Turns out if you basically do that, or this, tends to match that ring oscillator very, very well. Okay? And again, you can actually walk through some simple math why that is, but conceptually speaking, if you sort of think about it, one of the transistors in this oscillator is always either pulling up or pulling down. So if you sort of look at it across the whole cycle, the current being dissipated by that is basically the on current of some transistor inside of there. Okay? And by the way, I guess if you want, the derivation of that, you can take a look at a paper that I wrote back in JSC in 2006, or in my thesis as well. And I'll sort of give you this reference again in a second. Okay?
I have a very basic question. So for this way, what you're doing is like actually you want to improve the PSRR, but what if your load is also switching?
Ah.
So the actual load switches differently from the
Great
replica
question.
load.
So now you're absolutely right. If your real load is switching, this is not a good thing to do, right? Because if this is the thing that's generating the noise in the first place, then you probably don't want to do this, right? Because you've sort of broken the feedback from there.
So then what's the application for this type of regulator? Just VCO.
Okay, to be totally fair, you can actually use this in other places too.
Okay.
But as an example, imagine that you use this. So by the way, this is really the #1 application. That's where you'll see this the most often. but you can actually use it in other places too, even if the load is switching, as long as you know that the load is switching. So by the way, if you know the load is switching, what do you do to make it so that this still works very well? Yeah, you replicate that switching, right? So there's actually a paper by some of the Rambus guys, I think this was in VLSI 2007, that were doing exactly that. Okay, so they basically had this load right here was their data slicers. They basically had some dummy data slicers here that were replicating those variations. Okay? And indeed, if you do that, again, it works quite nicely for all of the same reasons the supply noise stuff did. But nonetheless, usually, one of the first things that people say is, well, how the hell do I replicate the load? Because I don't often, I don't always really know exactly what that load is. Now, okay, when you do it with the ring oscillators, that's actually pretty easy. But if you want to apply this in other places, sometimes that's a pretty tricky thing to do. In particular, if you want to do it on things like phase interpolators and stuff like that, that has some digital junk in there, not quite as straightforward to replicate. Well, the good news is, actually, again, if you just sort of keep in mind that basically all you're trying to do is just get things to match at DC, there's a very, very simple idea you can apply to basically fix exactly that problem. So what do you think? What do you guys think I'm going to do? How do you think I'm going to fix the unknown, the uncertainty there?
Can I just mirror the current and put it there?
Basically, yes. Okay. Now, it's not exactly just mirroring the current, because if I just mirror the current, then there's one other parameter that I'm not exactly getting right.
Yeah, average it.
Averaging. It's not quite that. So when I've done this trick right here, remember, there's really sort of two things that I could be caring about. So what two parameters, let's say I give you a particular bias point, a particular voltage. What two parameters do I actually care about from the standpoint of the IV characteristic at a given voltage? And I'll maybe, I don't have
the I and the slope.
There we go. You care about both what's the bias current itself and what's the incremental resistance, right? Because I need both of those to figure out, both to get it DC in the right spot and to make the sensitivity to the supply kind of the right value, okay? But indeed, actually, at least conceptually, what we're basically going to do is force those two things to be the same, okay? Now, it turns out in this particular case, I'm going to do that not by sort of, let's say, building a normal mirror, but actually I'm going to actively force them to be the same. Okay, and actually let me maybe give myself some more space here. Okay, so I'm going to draw this, and that really is a PMOS down there. I did not make a mistake, and I'll explain why I did that in 1 second. So the way I'm going to do that is something that looks like this. Okay? Now here you can again have some fun figuring out what the signs of things are. It turns out you want to do things that way. I'll explain why in 1 second. But so conceptually what I'm doing here is essentially what we just said. Okay? What I'm really trying to do is make sure that, okay, I know that if everything is right, basically these two voltages should be the same. Right? If at least the DC bias current is the same, these two voltages should match each other. Right? Because as long as this transistor matches that transistor, then if I get the right sort of scaled bias current here relative to there, everything should be good, at least in terms of the DC bias point. Right? That make sense to everybody? Or? Okay, so DC bias point, I'm good. Now, we just have to be a little bit careful because actually there's a couple of, let's say, minor but important details that I neglected there. So first of all, I added this cap in right here because remember, the only purpose of this loop is to get things right at DC, right? If I had a high bandwidth in this loop, actually I'll have a problem, right? Because what's going to happen is that this noise is going to be set by, this is going to track exactly that. And that defeats exactly the purpose of doing this, right? So the point here is, again, you really only do this at DC. Okay, so that loop there had better be slow. There's one other thing which I did for a particular reason here, which is, as I said, I really am making this a PMOS. Okay, in other words, I'm actually making that a source follower there. Why do you think I made that a source follower? As opposed to, for example, a common source. Yeah?
Is it because you have too much gain in the loop, so you want to reduce the gain or something?
Nope.
You want to couple to the ground?
Don't want to couple to ground? No, I don't think so. I mean, maybe, but I'm not quite sure I understand the connection there. What?
The impedance of that node.
Okay, I am lowering the impedance of that node, or I should say I'm doing something to the impedance of that node. Now, what were the two parameters we said that I needed to get right?
Oh, yeah, did you want higher bandwidth of that node?
No, so remember I said that when I'm going to copy this thing, there's two parameters that I need to get right.
Current and
So now the
AC
impedance is.
impedance.
The current and the incremental impedance.
So now if you have like the one over GM, the impedance is now functional.
Exactly.
Current going to it.
Right, so the reason I did that was not because I specifically wanted a quote-unquote low impedance. I'm just using this as my hack of trying to say that if I got the right bias current, to try and also get the right output impedance. Okay? Now, that's not to say that this works universally for all possible loads you can think of, but it turns out that if you sort of look at, let's say, a reasonable range of digital circuits, this turns out to kind of work out okay. Okay, it's not exactly right, but it matches well enough that it actually works reasonably well. Okay, and again, that just has to do with in a digital circuit, basically for the same reason that you can kind of think of the ring oscillator as just being a diode-connected device, where the current is just sort of flowing through that device. I'm just playing the same trick here. Okay? I'm just saying that incrementally speaking, the incremental resistance is also related to the GM of kind of the devices that are in that digital circuit there. Does that make sense to people? Or now, by the way, this is kind of a hack, right? Like, I'm not actively forcing it to be correct. If you wanted to do that, there's some other things you could do, right? You could, dink the current around and measure the slopes and try and, actively correct it. Usually that's not worth it. Usually this works reasonably well so that you can kind of get away with it. Does this make sense to people, or? Okay, so just one other quick note, because you can spend some time sort of trying to figure this out. The reason you want to put the plus and the minus like this basically has to do with the fact, or sort of conceptually at least has to do with, what is it that's the master and what is it that's the slave? Okay? So in this case, what should be the quote-unquote master is how much current is flowing in this load. Okay, that's the thing that you're really trying to replicate. Okay? So because of that, what this basically says is, if this load current changes, that implies, or let's say that this load current, decreases, meaning you're drawing less current than you were before. If you're drawing less current than you were before, that means this voltage will go up, right? So if I want to copy that effect, then I better make this voltage also go up, right? Does that make sense to people, or? So that's, by the way, the reason why I put the plus sign here. Okay? You can actually go through some more math and convince yourself that from a stability standpoint, that's really the way it has to be. But at least conceptually, if you get confused by these things, just always think about what's the master and what's the slave. Okay? So in this case, the current through that load is the master. Okay? The current that's through the replica, that's what you're trying to slave to it. Okay? Because this is the thing that's sort of known and fixed. This is the thing that you don't know and you're trying to correct. Okay? Does this make sense to people, or? Okay, so unless there's more questions on that, what I want to do is sort of come back and maybe point out one thing that's a little bit annoying about sort of this replica bias structure that we've been talking about. So as I guess you guys were asking, it seems like you can't arbitrarily do this, right? Like, it seems like maybe there's some special cases where this works out really nicely. Well, turns out the one special case where this, or at least the one most common special case where this works really nicely, is in fact in phase lock loops. And in particular in ring oscillator-based phase lock loops. Okay? So let's say I was to go and just replace that regulator that I keep drawing directly with this thing. Well, unfortunately, in the context of a phase lock loop, there's one thing that's pretty bad about this. The thing that's pretty bad about it is that, notice, I have no feedback whatsoever from this vreg. So we said, okay, fine, the loop will readjust and sort of find the right value there. That's okay. But the loop is adjusting this Vin right here, right, or this Vref. It's going to take time before that thing shows up at that output right there, right? Because basically I have a completely open loop system there, right? In other words, this decap is completely filtering out whatever adjustments I make here at any fast rate, right? Well, that's bad news, right? Because if I stick that inside of this regulator here, and that open loop output pole bandwidth is lower than like my reference frequency, I'm basically going to be introducing an additional significant pole into my loop, right? And hey, if I put an additional significant pole into there, that's going to limit my overall bandwidth. Or rather, if I still want to be stable, I better drop my overall bandwidth. Okay? So typically when you put this regulator into here, if you want your loop bandwidth to be like 1/10 of the reference frequency, that also means the bandwidth from there to there has to be about the reference frequency. Okay? And unfortunately, if you do something like this, that would drastically limit how much decap you could put there, and then also significantly limit how good of a sort of supply rejection you could actually get. Okay? Yeah?
Would a feed-forward path for this?
Okay, well, so basically yes. Turns out the way where I'm going to sort of fix this particular problem is just reintroduce the feedback that I obliterated in the first place. Okay? Now, that's not to say that you can, once you've reintroduced the feedback, indeed, you're going to do worse from a supply rejection standpoint than you could have done if you didn't have the feedback. But at least now you can get the bandwidth. Okay? So, we're actually out of time for today. I'll show you guys next time sort of in more detail how you do that. But turns out you can still get a lot of the benefit from the standpoint of the supply rejection, at least in terms of the trade-off now being linear. But you can still also make this work inside of the PLL context. Okay, so I'll see you guys next Tuesday.